Hello students, in this lecture we will talk about molecular electronics. And I will mainly focus on organic molecules used in molecular electronics. Now, organic molecules, they form a semiconducting interface. It can be used as a semiconductive interface. And there is a current-driven resorption taking place in these organic molecules. For example, cyclopentene. Can absorb silicon. One can be absorbed. This cyclopentene can be absorbed on silicon 100 surface, and after absorption it fully saturates. So there is one is absorption followed by saturation. So the next thing is that we should look out for the fact that it shouldn't dissolve. So it can dissolve, but the probability of desorption is very low. So desorption at reduced probability. Now this is for cyclopentene, but the desorption rate is again it depends upon a lot of things, like the desorption rate might not be same in other organic molecules. Like the desorption rate is very high if we compare it with benzene. It is absorbed on silicon 100, or with chlorobenzene. Absorbed on silicon 111. In these cases, the desorption rate is very high. So cyclopentene is an ideal candidate for molecular electronics. Now, the process of desorption, if we concentrate on the process of desorption, the desorption occurs via resonant attachment. That means desorption occurs by resonant attachment of whole electron. To the HOMO-LUMO gap. We'll take one class to explain what is a HOMO-LUMO gap in another class, but for the time being, there is a attachment of foreign electron, resonant attachment of foreign electron taking place, which is causing desorption. And so when we talk about molecular electronics, so the silicon organic molecule, they form a hybrid structure or hybrid system. And in this hybrid system, there is a reaction of small alkene molecules with silicon. We'll do it silicon 100, and it is through a process called surface Diels Alder process. So what happens in this process is that above 200 Kelvin, the silicon on which the organic molecules have been dissolved, it actually buckles the dimers. Now, these dimers they constantly oscillate due to thermal excitation. They constantly oscillate due to thermal excitations. And due to this constant oscillation, there is a partial charge transfer from one atom of the dimer to another. So it leads to partial charge transfer from one atom of dimer to another. Now the up dimer is negative, whereas the down dimer is positive. So the negative one is called nucleophilic. It gets attracted towards the nucleus, which is positively charged, and the down dimer, which is positive, is electrophilic because it attracts to the electron, which is negatively charged. So this is all about the surface aldase process. Now we need to form precursors. That means the initial material on which the devices, on which the final product is made. Now, in the case of these hybrid silicon organic molecule hybrid systems, precursors are formed when the carbon-carbon double bond it is attracted to the down diameter. And then there is a formation of two silicon carbon bonds, which are of course covalent in nature. So this is the first step, and this is the second step. Now, in this case, if you provide a 4 voltage sample bias, minus 4 voltage sample bias, so it will correspond to 2 nanoampere current, and it is used in the case of, it can be done with the scanning tunneling microscope. And we take cyclopentene, adsorbed cyclopentene on the silicon surface. So by providing these conditions, the electron can cause the stimulated desorption. The stimulated desorption can be caused by electron if we provide the following conditions. Now, how to detect a desorption has taken place? To detect the desorption, there is a feedback loop. It's called the second feedback loop. So it has two purposes. Firstly, it monitors the current. And by doing that, it can detect the desorption. The second feedback loop. Now, when the desorption is taking place, the parameter which signifies or which is associated with desorption is called desorption yield. Given as Y, and it is basically the ratio of the number of desorption events by number of electrons incident. So it's a number of desorption divided by the number of electrons incident. Now Y is equal to N T E divided by I. T, where NT is the number of molecules dissolved, I is the tunnel current, and T is the time spent by tip over the sample. So this is the desorption yield. The next parameter is called the desorption rate. And it is expressed as R, and R is simply equal to desorption yield into I by E. Now we know that Y is equal to ND E by IT. So we put that value of Y here. So it's ND E by IT into I by E. So this I and I cancels, E and E cancels. So that with ND by T. So this is the relationship desorption rate. So if we plot both the desorption rate and desorption yield with respect to voltages and with respect to current, 16 nanoamperes. So we can see that in the case of the desorption yield, the plot takes the following path. It is like this. So this is 0, this is -5, and this is +5. So 10 to the power -12, and this is 10 to the power -8, and while this is quite linear. So this is where the desorption is taking place. So this is where the desorption yield goes to 0. That means the first layer of the molecules have dissolved, and the second layer of molecules formation is taking place. So there is again, since we are applying, so there is again making and breaking of. So desorption takes place, adsorption takes place, again desorption, and it can be controlled by the voltage applied to the silicon cyclopentene hydrostructure. By the application of voltage, we can actually control the desorption that is taking place. So you can written in this form. So this is the silicon 100, and over which the cyclopentene have been adsorbed. Now we are taking a STM tip and we are giving voltage or current, whatever you may call it. So by varying the voltage here, we're making and breaking the cyclopentene. We can either allowing it to dissolve or allowing it to adsorb. So this layer is again governed by the voltage or the current supplied by the STM tip on the silicon cyclopentene heterostructure. Now there is a negative value of desorption. There is a threshold value and of desorption, and there is a both in the positive and the negative sides. So if you look at the threshold value, so it is minus 2.5 volts in the negative bias, and that is 3.5 volts in the positive bias. That means this value is minus 2.5, whereas this value is 3.5 volts. There is 1 volt in between, and the lower limit of the desorption yield Y is 3 into 10 to the power minus 12. And the units is events per electrons. Now, as we have seen that the desorption is induced by the STM tip, so the desorption can also be induced by electric field. So this is what we have seen. So desorption induced by one is electric field, it's called DIEF, desorption induced by electric field, and the second one is single or multiple electronic transitions. And it's called DIET for multiple electronic transitions, and DISET for single electron transitions. Now, single electron transitions has got a weak dependence on the desorption rate. So DIET and DIET, there is weak dependence of R on the current, whereas for DIMET, multiple electronic transition, R is proportional. There's a different color here. R is proportional to the power n, when n is much greater than 1. So there is a strong dependence of R on n. So n here indicates the number of inelastic scattering events required for the process to occur. So again, we write for DIMET, the desorption yield is proportional to I to the power n. N is greater than 1, and n is the number of elastic scattering. Events, number of elastic scattering events required for the process to occur. Required for desorption to occur. So from R versus I plot, we can distinguish between DIMET and DIET. Has it been a multiple electronic transfer or a single electronic transfer? Now this dependence of R on I is linear. This is linear dependence. So increase in current, the desorption rate increases, as we have seen previously. Now, this is about electronics. First lecture, we will catch it up with other electronics devices and systems later on.